Can you see the slides now?
Yes, sir.
So what you can see, choice of ground treatment technique, right?
Yes, the choice of ground treatment techniques.
Okay. So I'll just, so basically it's the last part of different ground treatment techniques. So basically what first day we discussed about the mechanical one and use different type of compactor and vibrator. And then also for the shallow depth, then we talked about dynamic compaction or blast, control blasting for the deeper depth. And then fiber compaction, fiber composer, all these different, compaction. Then we talked about the hydraulic modification, get rid of the water, and then the surcharge load, preloading, and then also when you accelerate the consolidation. Yesterday we talked about sand drain. We talked about prefabricated encrest sand drain, and then PVD drain. We talked about that, and then the chemical modification. And yesterday's we talked about different chemical admixture you need to use. The conventional admixture, cement and lime, and industrial waste, fly ash, GGBS, and other. And then you talk non-conventional, you can use polymer, you can use different geopolymer we mentioned, and then durability of that. And then the last part is this inclusion, something you include into the soil. And this is basically the soil nail is also inclusion, right? So soil nail is also, this is the last portion of this. Basically, you need to reinforcing the soil, either MSE. And so we'll talk a little bit of, first thing is we'll talk about highly organic soil, how to stabilize the organic soil, and then we'll talk about the retaining wall design. So for any ground improvement technique, stability of the technique, we need to check whether the soil and technique is fundamentally compatible. Technical compliance, does the technique provide strength and stiffness requirements? So also we need to check that. Is the material is readily available? So also we need to check that. And the cost is within the budget, or what is the cost of time? So how much time is it delayed or accelerated one? So that's also need to check. And also you see that environmental considerations. So that is very general choice of ground improvement technique. So now I'm going to talk about highly organic soil stabilization. Okay. So can you see the slide now? Highly organic soil. Can you see the slide? Highly
Yes, sir.
organic soil. Okay, good. So
Yes,
highly
sir. Yes,
organic
sir.
soil. Okay. So highly organic soil is when the soil, most of the time, when the soil, in a soil, the organic content is more than 20%, we call it organic soil. Okay. For any infrastructure design, construction, if it is more than 20% organic, we generally avoid it. Either we remove it or replace it with good soil, or, we cannot just use that. So our problem is our very highly organic soil or peat. And if the organic content is more than 75%, it's called the peat as per ASTM 2067. So that is much more challenging how to construct that type of soil, because the soil is very soft, is wet, and very low shear strength. So highly organic soil or compressible soil, you can found anywhere in earth except the barren and Arctic region. And mostly it is covered like a 5 to 8%. In India, there are different places, the greater Pamba basin of Kerala, Assam, Manipur, northeastern state, some part in Kashmir or Western Ghat or Sundarban Delta in West Bengal. US, mostly the Michigan area, Minnesota, Florida Everglades, and some part in California also, they have these highly organic soil or peat. In tropical peat, generally in Malaysia, there is 3.3 million hectares of 8% of the land area is also peat. So here, so the soft soil or peat, this is a picture from Malaysia. So mostly they do, that's like a water slurry. How to construct in this type of soil, it is very, very difficult. So most of the time, what they do, say use a bamboo mat, and then just like add as a temporary reinforcement, and they put sand and gravel on the top of that. So, but soil is so soft, so sometimes you just add material and just sinking. It's so difficult. And I know there is a town in Malaysia, is in West Malaysia, East Malaysia, in Sarawak, in Borneo Island. There is one town is basically they constructed everything on the construction on pile, everything is good. Remaining structures, everything is settled. And that town is really abundant now because too much of settlement, all the that utility pipes and everything is settled, and people cannot use it. So the ground improvement method. So I'm going to talk about like a peat soil stabilizations. One of my graduate students used while I was in Malaysia. So here, this is if the depth of the peat soil is very 1 feet or 2 feet, 1 feet, you remove it and fill it with good sand. The replacement method, correct? So remove and replacement methods. But sometimes the peat soil depth are really is quite thick, so it is not economical to remove whole soil. So obviously, if you want to construct on this type of soil, you see the sinking excavator. So even excavator cannot, it can take the load of the excavator. So the problem is, if you want to put any structures, good structures, you need to use pile foundation. So but sometimes it's obviously pile foundation is expensive. So people are if the soft soil is very high depth, so you can stabilize some portion of the soil if the water content is less, and then you can use this chemical soil stabilization technique. The problem is sometimes the water table is too high. Sometimes you need to pump the water out and then reduce the water content, and then you mix it. Or sometimes you take out the soil sample and then mix it and then dump it there. There are different techniques I have seen there in Malaysia. So the pile embankment is expensive, but lightweight field, sometimes the soil strength is so low, so we need to use some lightweight field over there, okay? And also the thermal precompressions also can be used. So I'm going to talk about here chemical soil stabilization techniques. So this is how the sample looks like, So when you collect soil sample, it's very soft and the water content is very high, okay? And then soil has a lot of fibers. So mostly is decomposed organic matter. So mostly if you want to do experiment on that type of soil, you cannot just keep it in the oven. First, you have to put it in a tray for sun dry and then keep it in the oven. Also, sometimes for this peat type of soil, because organic content is too high and the fiber is there, instead of 100 degree, for the moisture content is 105 degrees Celsius for 24 hours, you need to reduce the temperature like 65 degrees, otherwise it will burn. So 65 degree for 24 hours, and then you grind it and pass through 3.3 millimeter sieve. So it depends how much fiber you need. And then you do for different tests. So we collected the soil sample and then we grind it and then oven dried, sun dried first, and then oven dried for 60 degree, 65 degree, and then test different tests. So basically, physical test and geotechnical properties test has been conducted. Natural moisture content, degree of, so here it is a little bit different from the normal soil. One is the degree of decomposition of the test and the fiber content test. Generally, we don't do this for normal soil. And also we do loss on ignition and organic content test, and also do the pH test. So these are the different tests generally you need to do for organic soil or peat soil. Geotechnical properties in the standard Proctor and UCS is common, and then also compressibility test, that is the consolidation test, because it has a fiber. So if you use normal odometer test or consolidation test, it will not give you the correct results. So you need to use the bigger diameter cell called the row cell, and there is a cell, bigger diameter cell, and then you need to use a large quantity of sample, and then there is a rubber balloon. You can pressurize using rubber balloon, and then consolidation takes place. But advantages of that also, you can measure the pore water pressure from this consolidation test, the row cell consolidation test. So these are the different tests, different sample we tested. So we designated M1, M2, M3 to M8. And you see the first, second row, you see the natural moisture content. You see the moisture content is 587, 600, 400. So this is not a soil, correct? This is like a slurry. So how to construct on that type of soil is a big challenge. So then degree of decomposition. So it is H1, so there is a scale from H1 to H10. So more number is more decomposed. More number is more decomposed. So here in this soil, M1 to M8, so M8 is the more decomposed, So what is going to happen if it's more decomposed and finally is after decomposed, it will be converting from organic soil to mineral soil, right? The loss on ignition is initially was this 96 for this one, M1, and 44 for this more decomposed. The loss on ignition is also decreasing. Organic content here, M1 is the highest numbers, 95. So this is definitely peat soil because the organic content is more than 75%. So M8 is over here. This is 42%, 42.53%. Specific gravity you see over here. Organic content is fiber is more fiber. The specific gravity is lighter, but you see is more decomposed. It is converting from organic soil to mineral soil. The specific gravity is increased. Fiber content is also decreased for more decomposed. Initially, for peat, it was 65%, almost 66%. For M8, it is 31%. Liquid limit, you see here, liquid limit is, you see 150%. 150%. And then for M8 is 69. And then pH, one thing you noticed here, the pH is less than 7. So it is acidic. Okay, the pH is less than 7 is acidic. So if you want to stabilize using chemicals, so then we need alkali, right? So for the lime or cement, we need alkali. So if it is acidic, then it is not going to work, right? So what you need to do, you need to add more cement or more lime, or you need to do some treatment, make it like a neutralized, add some alkali treatment, and then you do some cement or lime or any other fly ash, So in that way, you are, the result will be much better. And then also, as I mentioned, so this is the fiber content for this organic soil. Depending on the fiber content, we call it the different types of peat. We call it fibril peat, we call it hemic peat, we call it serpic peat, different type of peat. And how to calculate the organic content? Organic content is given by this equation, 100 minus C times 100 minus N, or C is the correction factor, generally used for 1.04 as per given by the EDIL, and the N is the loss on ignition. So you can find out how much is the organic content. So this is, I'm not going to go in detail. So this is the degree of humidification. It's a very crude test to find out how much is the degree of decomposition. Most of the time, you take a peat soil from the side and just squeeze it. So what type of water is coming out from here between your fingers? So you can find out what type of the degree of decomposition. Okay. So there are 10 H1 to H10, and this is called the von Post scale. Von Post scale. So you can find out what are the different category. So the H10 is completely decomposed peat. So no plant fractions, and when it's squeezed out, so it escapes the peat weight scrapes between the fingers. So again, weight peat is coming out. So sometimes depending on the fiber, content, or depending on the degree of decomposition. So depending on what type of water is coming out, only water is coming out, the peat is coming out. So all these things you can find out from there. So now, as I mentioned, we did a compaction test for M1 and M8, all these different type of soil, and then we noticed that the more decomposed material, and the specific gravity was higher, and then obviously the standard Proctor, the specific gravity is higher, means it will give you more density. So M8 was, you see over here, M8 was more decomposed. Specific gravity was 1.82. That's why it gave the maximum strength. So M8 is start over here. That is the maximum strength it can give, maximum dry density, but the optimum moisture content is also less. Okay. Then, so this is a sample collection we did. This is two of my graduate students that time. So we fabricated this. This one you see here. This is the soil sampler. Okay, we fabricated that and to collect the soil sample. And on the left corner over here, this is the row cell for the consolidation test. Okay, so and you have to really transport very slowly and then bring it and place it into the row cell to do the test. So this is the sampler we fabricated. So basically, just like a syringe, injection syringe. So basically, there's a plate over here. If you push it into the soil and then you just drag it up so that it would create a vacuum and then hold the sample because it's so soft, it is difficult. Then these are the different properties of the row cell consolidation test. You see over here, so again, the type of peat, as I mentioned, there's a 5-week peat over 66%. If it is over 60% fiber, then it's called the 5-week peat. If it is 33 to 66% fiber, then it's called the hemic peat. If it is less than 33%, it's called the sulfic peat. There are different type of peat. And then bond pore scale, it is H4 or less in this case, and H4 or H5. If it is sulfic, then it is H7. So, and then we did all the different tests. And then finally, we did the consolidation test over here. You see here, void ratio is 10. So most of the time, the void ratio is 1 and less, right? If it is a pure clay, it is a little bit more than 1, right? So the void ratio is 10. So it's very, very compressible. And this is using odometer test. This one, the same test using odometer, and same sample using the row cell consolidation cell. So you see the compression index values. Compression index values is the row cell is 3.48. And then odometer value 4 point something. It's a compression index. It will give you, so settlement you can calculate from the CC value, correct? Settlement is basically CC times H divided by 1 plus E naught log of 10 plus sigma naught plus delta sigma divided by sigma naught. You can find out from there. So basically CC is important, right? So CC is the compression index. Compression index more, it will give more settlement. So it's very high. Most of the cases, compression index is less than some fraction. So now it is 3, 4. This is really extremely high. So compressibility index, that's why we just normalize that compressive index values. And then also peat soil, it is very important to calculate not only that primary consolidation, we need to calculate for the secondary and tertiary consolidation. Okay? And this is the relation between this compression index, primary consolidation, and the secondary consolidation over here. And you see the secondary consolidation is almost 1/5 of this, or 1/10 of this, the compression index. Okay. So, and then, so basically what we did in this is the properties of the peat soil. And then we did all the basic tests, and then we stabilized that to increase the strength grain. So here we used different types of chemicals. So most of the cases, the chemicals is the fly ash, lime, all these different chemicals, and we used different sodium sulfate, and calcium chloride also. So here, this is the curing period. So you see the cured, when you prepare the soil sample, it cured under water. Just to simulate the situation, the peat soil has very high water content over there. So this, all the mold is half submerged. And then, because the soil is so soft, even the excavation, if you push it, the soil will come out. It will be brittle. So that's why we developed we put it in it's split into two, and they just push it using this spatula, and then divide it into and collect the soil sample. So, and then we measure the soil sample, and then we test it for UCS test. Basically, it's 50 millimeter times 100. So for that particular peat soil, we used ordinary Portland cement, 5 to 25%, because the organic soil you need a little bit more compared to the mineral soil. And then we use quicklime, 2 to 8%. We use fly ash, 5 to 25%. and we use combination of fly ash and quick lime. So you use 5, 10, 15, 20% fly ash, and then we just varied this 2 to 8% quick lime, for different combinations. So this is one. And then we just check how much is the original strength of the UCS strength. So we have that. And then how much is the with time, that 7 days, 14 days, and 28 days, how the strength is increasing. Obviously, you can see here, this is the left side is the lime, and this is for the different type of cement. So obviously, the more cement, 25% cement, the strength is high, but this is the lime. Strength is almost close to 10% cement. Then this is the graph with combination of this is the original fly ash. This is the combination of fly ash plus lime. This is also the combination of fly ash plus lime. What is happening for different combinations, and we have seen that with the fly ash content is increasing, the strength is increasing also. So not much, but a little bit increase. And then this is the scanning electron microscope of original peat soil. This is original fly ash, looks like. And then when you have the 20% fly ash and 20% fly ash plus lime, so you see is more dense structures, and the strength. That's why the strength is increasing. UCS strength is increasing. So over here, in 20% cement, you see is the strong bond form. Because of that, this is 5,000 times magnified, and this is 5 micron. So that's the reason the strength is increasing for the cement. And these are the conclusion for that test. So basically, over here, the result is the peat sample increases 5 to 10%. But so when you use, so I'm just going to go here, that when you use 5% OPC plus fly ash, and 2% calcium sulfate stabilized soil better than the chemicals we used. And then also, when you use like a 20% OPC, and when you use 6% lime and 20% fly ash, that will give almost 70% strength when you use 20% of cement. Okay. So the first here, this is the untreated one. So these studies I have not presented here. This is one of our other studies. What we did, because of the fly ash, that the peat is basically is acidic because of it has humic acid and fulvic acid. We neutralize that acid with sodium hydroxide first, and then you add it with different chemicals and different stabilizers. Also, that paper. So basically over here, you can find out all this, whatever I just now presented in this journal paper. And I have some more, but I have not included over here in this. Okay. So this is basically now the organic soil stabilizations. Then I'm going to talk about now the earth structures or earth retaining structures. Okay. So again, this is totally the last topic. Basically, we're talking about earth retaining structures or MSC wall design. External stabilized system, that's the in-situ wall, the gravity wall. Internal stabilized system, that's the reinforcing coming into picture. So reinforced earth, or it can be used geotextiles material. We'll talk a little bit of geosynthetic material. And then in-situ reinforcement, you can use soil nailing, you can use reticulated micropiles. So micropile is basically another one type of soil nail, smaller diameter piles. So obviously now, this is the last method, as I mentioned, the soil stabilization is something you need to include into the soil, because soil cannot take tension. So what you need to do, either you include some reinforcement, or you can use some geotextiles or geogrid, okay? So that it can take the tensile load, soil can take compression load. So that's the MSC wall. So, so therefore, the inclusion of tensile force member in a soil can significantly increase the strength and load bearing capacity. Okay. So soil can take only the compression load. So again, the resulting in the reinforcing soil is called the mechanically stabilized earth. Mechanically stabilized earth. So obviously we can design mechanically stabilized earth retaining wall, right? So often MSE is used in slopes when the slope is steeper. So if you use a mechanically stabilized earth, you can make a really exact vertical wall, so that you, instead of if you make a slope, so you can lose some space. So here you can use utilized whole area. This method of intermediate alternative between the earth slopes and the retaining walls. Retaining wall or reinforcement. So I'm going to talk about a little bit more about the reinforcement. So here, and then also we talk about what are the different reinforcing material used to stabilize the soil. So modern form of reinforced earth were introduced by the Henry Vidal in 1960. Reinforced earth is internally stabilized, flexible structures to assist dynamic and structural load and the foundation movement and settlement. So advantage of MSE retaining wall or any structures is it can resist more dynamic or earthquake load, and the construction is much quicker compared to the conventional retaining wall. So reinforced soil or mechanically stabilized soil is a construction technique that consists soil that has been strengthened by tensile strength. So the soil can take on compression. So you need to put some metal strip, you need to put some geotextiles or geogrid. Okay. So reinforced earth is the type of retaining wall. The mechanically reinforced earth is also called the gravity wall. So these are the few things. And again, reinforced earth is a combination of soil, which is strong in shear and compression, and reinforcement, which is strong in tensile strength. So that's the reason you can use, so basically the solid structures. Okay. So beneficial effect of soil reinforcement, so increase the tensile strength of the soil mass, that is one. And then the shear resistance developed from the friction between the soil reinforcement pressure plus water pressure. So advantages, as I mentioned, is the flexible structures. It can deform, withstand deformation and foundation settlement. And equally suitable for good foundation. Due to their flexible structures, it can withstand, as I mentioned earlier, earthquake stress better than the conventional rigid structures. Reinforced structure can be constructed speedily and also in stages. It can do in construction stages, or you can do the construction very quickly. Reinforcement, particularly geotextiles fabric, as a lightweight and available for convenient sizes. It is a factory product, so you can lay that. It comes in a roll, so you can do the construction very quick. And reinforced is structures economical, giving 30 to 50% cost when compared to the conventional concrete and retaining walls. It's less expensive. So you can use either a different type, or you can use either metal years quickly, but for the temporary, you can use that for temporary structures. Okay, and also you need to do some treatment. So now, if you're using metal strip, obviously, when you're designing it, you need to either use the galvanized steel, or you need to use some painting to prevent corrosions. So galvanized steel is used as reinforcement, and the corrosion we are designing, you need to use that. Obviously, the corrosion is inevitable. So you need to use like a 0.25 to 0.05 millimeter per year. Everything, every time will be, every year will be corrosion rate. Actual thickness, that's why you need to do the design thickness plus R, the rate of corrosion you need to include, and how much is the lifetime of the structure. So mostly, generally we design for 30 years or 40 years. Although we know that metal strip is going to deteriorate, people in US, at least I know, people still use metal strip instead of geotextiles or geogrid. So I'm just going to talk a little bit of geosynthetic material. Geosynthetic materials, the balance. I'm not going to go in detail over here. Drainage, filtration, separation, and enforcement. There are different purpose. You can use that but here in this case, you'll be using as an enforcement. So, and then there are geotextiles and geogrid and geomembrane. These are the three main geosynthetic material. It comes in geosynthetic materials are geotextiles, geogrid, and geomembrane. So textiles means it's like cloth, right? So again, it can be geosynthetic material. It can be polyester, can be polystyrene, it can be polyethylene, it can be polyacrylonite, it can be polyvinyl chloride, PVC. So any type of material, so it can be high density or low density polyethylene material, synthetic material. Okay, so it can, people are using also natural fibers like a cotton. So over here, uh, there are oven geotextiles. There are different types, like a oven and non-oven. And there are different types of geosynthetic material. I will just go quickly. Geotextiles, it can be geogrid, it can be geonet, it can be geomembrane, geosynthetic clay liner. So there's the clay, bentonite clay, and then the top, there is geosynthetic on the top. Geopipe, geofoam, geocomposite. So there are a lot of things. Geofoam generally used for peat soil. Just for example, people are using like a geofoam or foam concrete on the top of stabilized peat, because the strength is very, very low, that bearing capacity. Geotextiles, it looks like this is the cloths, is the the pattern is there, oven filament. Okay? This is non-oven. So geogrid here will be using that mostly for retaining wall design. So it is looks like this geogrid. So it can be uniaxial, it can be biaxial. Most of the cases it is high density polyethylene type of material. So you see here, this is geogrid. There are different company has different geogrid, mostly used for reinforcement. So this is geonet, how it looks like. This is geomembrane. So basically for the containment, so water really permeability is water is like a mechanically stabilized art. So we have MAC reinforcement. It can be metal strip, it can be geotextiles, it can be geogrid. And then there's the drainage layer, and there's the facing wall. The facing wall is the prefabricated concrete blocks just attached to that. And that's why this construction is very quick, you know. So how it looks like, reinforced zone over here, this is drainage layer, reinforced zone, this is the retained zone over here. So most of the time it's a normal conventional wall, there is a retaining wall, and there is a backfill, right? So here, even these constitute the wall itself. So basically it's a reinforced zone, and then the next one is a retained zone, basically. So while doing the stability of these retaining walls, so we need to see the internal stability and then external stability, okay? So here the MAC wall is, you see approximately 57% MAC wall conducted in the US utilize the metal strip. Although we know that it's going to corrode, but still in US, 57% uses steel metal strip. Service life is doing this designing consideration of the retaining wall. So we need to check, as I mentioned, the conventional retaining wall. We do the external stability analysis to find out the factor of safety for because of the lateral load, how much is, whether it's going to overturn or whether it's going to retaining wall is going to slide, or is the bearing capacity failure. 3 different factors of safety you need to calculate for conventional retaining wall design. Here in this case, we need to do the external stability and we need to do the internal stability also. So internal stability checks involves the tensile strength and pull-out resistance, and the integrity of the facing element. So obviously you put an reinforcement inside this. If the reinforcement breaks, so then what is the point? So that is the tensile, determine the tensile strength. Then you need to find the pull-out resistance if it slips. You know, the same thing we mentioned for the grout anchor. And also integrity of the facing wall. Also, you need to check that, okay? And then external stability is the same as overall overturning, sliding, and bearing capacity. So this is how it looks like, MAC wall. So this is sliding, whole thing is sliding, whole thing is overturning. There is bearing capacity failure and deep-seated failure. So mostly the concrete block. And then there is a tie over here, and this is the horizontal spacing SH, and this is the vertical spacing. This is how it looks like, retaining wall for the metallic strip under construction. So mostly you can see here, the metal strip is there, and then you compact it with the swab. Okay. So, and then this is another geotextile. So put a layer of geotextiles, then put a sand layer, and then compact it using vibration because it's granular swab. And then after you compact it, and then fill with soil, then put another layer and compact it, then put another layer like this. So this is geotextile reinforced retaining wall. On the facing wall, you can see how it looks like. So if it is a geogrid, or sometimes you put a gabion wall, the facing wall, so it's like a cage type of structure. So put so this is a geogrid, and then how the facing wall looks like this, the concrete, and then fill it with sand or gravel, material and then put a layer of geogrid or geotextiles on the facing wall and then put another layers like that. So this is again over here in Southern Illinois. I took some of the pictures how it looks like. This is a metal strip, and then also there is a concrete facing wall over here. So concrete facing wall, how it looks like. This is over here. You can see here there is a connector, just like this. There's a groove here. The metal strip can go inside and then put a nut bolt there. So this is, you can see the horizontal spacing over here. How it looks like there is a holes that can be attached. So you can see here, this is the reinforcement strip, and this is the gravel type of material they used. And this is the horizontal spacing over here, from here to here. And this is the next one. So when you now, after this, they will fill it with the granular soil. And then the next one will be attaching on this groove over here. So this will come horizontally. So that will be the vertical spacing. And this one, you can see the horizontal spacing. This is how they do with this MSC wall. So this is the concrete block already. So you can see now this is the horizontal spacing. From here to here is the vertical spacing. And then also the concrete facing wall. Can be anything. So from the outside, it looks like this. So there are different, this is very common these days everywhere anywhere in the world now. So it's MSC wall design. So you can really construct a vertical wall. Okay. Reinforcement should be beyond that failure line, otherwise it's not going to work. And then finally, the total length of the reinforcement, you need to calculate LE plus LR. You need to calculate the total length. And again, you need to know how much is the active arc pressure, how much is the surcharge load if there is any. You need to calculate. And you need to know if there is a load, how much is the load distribution from there. And I'm not going to go in detail. So here, and then first thing is you need to know the tie force. How much is the tie force developed on this? So depending on the active arc pressure, area of the wall to be supported by the tie. So again, you need to the retaining wall design. When the wall is moving out from the soil, that is the active pressure, and the pressure distribution is like a triangle. So from the top is 0 and it's going down, and then the lateral arc pressure, the total pressure at the base of that retaining wall is gamma times how much is the height of the wall, and then one is the factor of safety for the tie failure. So you can find out the factor of safety, the breaking or tie of the tie. So you can use this equation where W is the width of the tie, T is the thickness of the tie, width of the tie, thickness of the tie, if Y is the tensile strength or the yield strength of the tie material. And this is the one we just calculated how much is the active stresses and the horizontal spacing and vertical spacing. So this is the factor of safety we can calculate against tie failure. And then this is the internal stability. And then reinforcing try how much is the friction between these reinforcement and the soil itself. So you can calculate by using FR how much is the effective length, how much is that the width, how much is the vertical stress, and how much is the sigma. You see here, sigma mu is the soil and type. And then you need to find out the total length, as I mentioned, the failure lines, how much is the inside the Rankins, LR, and how much is the length for the LE. So same way you can calculate how much is the total length. You need to know that LE plus LR. So LE is given by this equation. That is the effective length. That is the one, when there's the friction is important over there. And then LR, you can calculate, using this equation, H minus Z divided by tan 45 plus 5 by 2, 1 by 2. So the total length will be LE plus LR. There's the last equation over here. So we can find out the total length. So what is the step-by-step design procedure? So we need to know how much is the height of the wall. We need to assume internal stability. You need to assume that the factor of safety for breaking, factor of safety for the pull-out. As you go down below the ground. So basically, and that very much more economical. So again, you need to find out. So find out the taking at the moment at point B, and then how much of the load is coming, how much is the load for this area, how much is the load for this area, and then you can easily find out how much of the lateral load is coming. Also, you can calculate. So exactly the same way you did for factor of safety for sliding, how much factor of safety for bearing capacity, all these things you can easily calculate. So idea is basically you need to calculate the braking, factor of safety of braking and pull out. That is the internal stability. And external stability, the same thing for the conventional retaining wall design, factor of safety for the sliding, overturning, and the bearing capacity. So now this is for the geotextiles material over here. So earlier was a metal strip. This is a similar thing. But only thing is we need to, again, this is the allowable tensile strength. You can find out from the ultimate tensile strength. And then also you need to find out the ultimate reduction factor for installation damage. Sometimes because of this geogrid or geotextile material when you're installing, and that may create damage. So that's why you need to do some reduction factor due to creep, reduction factor due to chemical and biological degradation, and all these factors. There is a standard value from the Kroner 2005. So you can find out that. And then obviously when you use the geotextile, there should be some lap length over here, and there should be some lap length. So basically you see over here LL. So basically when geotextiles, put a geosynthetic material, put a granular soil, and then you just put a little bit of lap on the cover, overlap the cover. There is no skin over here. And then you put a layer of sand layer again, and then put a geotextiles, and then put the lap length over here. So basically what you need to do, you need to find out LE and LR, same, the Rankins failure lines, and then 45 plus 5 by 2 angle. And then, so this is geotextiles. The only thing is here, you can do same way exactly how much is the T allowable. And then the vertical spacing, you can find out how much is the factor of safety for breaking, 1.3 to 1.5. And the friction angle sometimes between these geotextiles and the angle of friction. So most of the time it is not given. you can use like a 2/3 of angle of inflection of the granular soil, so you can use that. And then again, LR is equal to, you can use this equation, LE is equal to use this equation, and then total length of the geotextiles LE plus LR, you can easily find out. So only thing is here, how much is the lap length? That one you can use this equation over here. Is SV, you need to know how much is the particle spacing, how much is the factor of safety for pullout, and then angle of initial friction for these, the geotextiles and the soil backfill material. And it should be minimum 1 meter. It should be minimum 1 meter or 3 feet. Okay. And then if you know that, and then again, the same way you can calculate the external stability one. Okay. So again, the external stability is basically the factor of safety against sliding, factor of safety against overturning, and factor of safety against bearing capacity failure. So, so that's all mostly, for this MAC wall design. All right. Any questions? Anything? So I have not solved any problems. This is just, the theory is very easy things, imaginary failure line and conventional retaining wall design, how much is the active pressure? So we need to, again, in the conventional design basis, how much is the lateral arc pressure? So you need to know how to calculate that, and easily you can find out. Okay.
Sir, there is one query in the chat box. In which field cotton geomass are used?
Which one?
In which field cotton geomass are used?
Okay, cotton one is not very common. I know that people are using for the temporary. I know that people are using for like a bamboo mat or jute geotextiles sometimes. And it's very rare. People don't use much. So yeah. I mean, although in the slide I mentioned, but I think it's not very common. And depending on again availability of the material, people are using also different types of fiber, right? So into the soil, so high density polyethylene fiber, people are using sisal fiber. There are a lot of fibers. Also, the coconut coir fiber, also people are using as a reinforcement. Is a disintegrated fiber. So a similar type, the cotton geomass, or but it's not easy to make. But I have seen some paper people mention that. But the cotton fiber, I think people are using in India. I know. And then also the bamboo mat. Also, I've seen in Malaysia people use that bamboo mat fiber or bamboo mat also for peat soil separation and other. So again, depending on the situation, you can use. So most of the cases, as I mentioned, in US, mostly people feel 57% uses the metal strip. It's easy. And then geotextiles and geogrid also people are using that. And then I know that geojute people are using long back, maybe 30 years ago. One of my friends, he uses in West Bengal, I know the geojute reinforcement in certain area. Any other question? Anyway, I have to, I just gone just very quick, to cover all this topic. But
Sir, someone was asking for the slides. If you can share, sir.
yeah, I think I can send if you can create like OneDrive or something, I can share all my slides, whatever I have, and then you guys can share to the participants.
Yes, sir. Yes, sir. You can please share to Chore, sir. I'll share in the to all the participants.
Yeah. Please do that. And then it seems like I need to prepare some quiz
Yes, sir.
for Saturday, correct?
Yes, sir. Yes, sir.
So, so that will be, I think, yeah, these slides will be required, but I'll be just only objective type on filling the blanks type question, correct?
Yes, sir.
Yeah. So only A, B, C, D type or fill in the blanks and, covering everything. So there'll be several questions then. I don't know how many, maybe.
Uh, Sir, I think 20 to 30 questions will be enough, sir.
20 to 30 questions from all topic? Yes.
Maybe, sir.
I think maybe 50, at least 50 to 100 maybe.
Okay, sir.
For every topic, at least 10 questions. Maybe.
Yes, sir.
Okay. I mean, very easy, but
We'll discuss that on tomorrow, sir.
yeah. Okay.
No question, sir. Actually, no question, sir.
Okay.
Everything is, yes, self-explanatory. You are explaining well.
Okay, good.
Thank you, sir. Thank you, sir. Thank you.
Already, so next, tomorrow is the only one class lecture, I think, is on sustainability of engineering and then sustainability improvement.
Yes, sir.
And that's all. Okay. And then we will talk about more about the participants. I don't know who is the participants even. All right. Thank you so much.
Okay. Thank you, sir.
Thank you, sir. Thank you.
All right. Thank you. Good night.
Good night.